Showing vectors in 3 dimensions is somewhat difficult a lot of times. Here I have a vector drawn in 3 dimensions. It's going from the origin to some point in space. This vector, I'm actually controlling with the magnitude and magnitude. We can change the vector. Magnitude is represented by its length. And its direction in 3 dimensions, we're actually controlling it with 2 angles. So we have angle theta y and an angle phi. Now to help see this vector, a lot of times if you have an application like this, you can actually move it and you can kind of see the vector. We can actually start it spinning so that you can see the vector a little bit better. There's actually 3 different ways, but maybe it'll be better to show those after I get the next step, because I want to show you where this angle is. This is the angle theta y, and it goes from 0, having the vector point right up the y-axis, to 180 degrees, where the vector would point directly down the y-axis, or in the negative y direction. So that's theta y. We also have the angle phi, which we put in the xz plane. So phi goes from minus 180 degrees to positive 180 degrees. So phi, you can see, is in the xz plane in this case. Again, that's not always true, so you got to kind of look at the angles that are given and drawn. We can use different ones. Okay, let's draw a rectangle here along the y-axis and out to the point. Here's this rectangle. We can see it's made up of 2 triangles, 2 right triangles. So we can look at this edge now, this edge, and find the magnitude of that edge. It's fairly straightforward. We see that this magnitude Fy is the magnitude of our vector times cosine of theta y. So that's the magnitude. And we can also find the magnitude of this edge of this rectangle here, which we'll call FH. So this vector is another vector that's in the xz plane. If I move a little bit, you can see it's in the xz plane. And again, we'll call that FH. Now this FH vector, we see we can draw a rectangle here. And again, now we can look at the edges of this rectangle and compute the length of the edges of the rectangle. So this Fx, and this is really the projection of our FH vector onto the x-axis. And we can project with the cosine of this angle phi. And likewise, we've got the opposite side here, and we can draw that to calculate our Fx vector, or Fz vector. So these Fx, Fy, and Fz are what we call the components of our vector f. And again, you just have to look at what angles are given in order to find these components with sine and cosine. Now we can add these three component vectors by moving them so that they're tip to tail. So we can move the FZ axis there and FY over here. Again, I think this makes it view relatively easier to see where the vector is pointing. Now let's look at some different views. I haven't done the views yet. This is a orthographic projection, which in its default view here is at 180 degrees or 120 degrees apart for the axes. We can use an oblique projection where your XY plane is your normal two-dimensional XY plane. Then we have the third direction coming out at an angle 45 degrees down here. And another thing to remember is that the axes may be labeled differently. We can have XY in this orientation, or we can have X coming out towards you here, so to speak, and Y and Z being the two-dimensional plane, or still another view, X and Z goes down and Y comes out towards you. Another thing to notice is with these axes, X, Y, and Z, is the right-hand rule. If you take your hand and you point it in the X direction, and then curl your fingers towards the Y direction, your thumb will point out in the Z direction for your right hand. This is what we call a right hand orientation, and we will always have a right hand orientation to our axes. Here we have another vector. Now I've got the X and Y plane horizontal. This vector I'm controlling with these components now. So I'm adjusting these component values. To change this vector. Again, we can look at it, rotate it a little bit, and you can see it better. I've added a grid here to the XY plane to help see things. That's usually not in the drawings. Sometimes I'll have a surface that may help you visualize it. Dashed line is below the surface, so let's get it above the surface. Okay, but I'll leave the grid on and turn the shade off. Again, we can project this. We see our Vx vector and our Vy vector we're going to add, and our Vz vector. So we've got the same kind of orientation that we've had before. I hope you're getting used to looking at these three-dimensional drawings. It's difficult for some. But now we know that this vector, V, the book uses bold letters to represent the vectors. So V is a vector in this case, and I is a vector of length 1 going in the x direction. J is a vector of length 1 going in the y direction, and K is a vector going in the z direction of magnitude 1. So if we multiply by the magnitudes of these projections, again, these letters are not bold, so they're just numbers. We can add these together and get our vector. In MATLAB, which we'll try to get you to use, you can write a vector as an array of 3 numbers, a 3-dimensional vector. We'll find this very convenient to do that. But now that we've got the components, Vx, Vy, and Vz, we can compute the magnitude of the vector. So there's a relationship here. Now, essentially the magnitude squared equals the sum of the squares of the components. So if we're missing one, we can find it with this equation and some algebra. But the convenient thing, or the thing I really want to talk about now, is this unit vector. This unit vector we call lambda. So if we divide our v vector by our magnitude, we get a vector whose length is 1. So our v vector can change size, but our direction vector, lambda, stays of a magnitude 1. Which is important because now we can use the direction of a cable or rod and relate then the magnitude of the force in that direction to the magnitude of the forces in the other directions. We can think of this unit vector, if we move it around, it will stay on the unit sphere. So it can point in any direction, but the tip will be on that sphere, if you want to think of it that way. The unit vector also has components, lambda x, lambda y, and lambda z. And it's interesting if we change, let's do Vx is small here. If I make the x component bigger, make the x component bigger, we see the other 2 components get smaller. And make the x component smaller, and the other 2 components get bigger. The numbers may be negative if you're pointing in the negative direction. Again, the sum of the squares of these components is 1, so it's magnitude 1. Now, we can actually now go in reverse, sort of. If we say we know that cosine theta x of this lambda x turns out to be the angle, again, between the x-axis and our vector. And similarly, we can kind of rewrite it and solve for theta y is arc cosine Vy over V. Again, that's our arc cosine Vy over V. In MATLAB, for arc cosine, it's a cos, and then d makes it in degrees. So our arc cosine functions in MATLAB are a cos d. Let's see, let's take a look at this theta y. So here we can see theta y. And these will go between 0 and 180 degrees. And theta z. So these three components of theta define the direction of the vector. Again, we only need two of them because we can always calculate the third because of the sum of the squares.